All right, everybody, welcome back. We're here for more from Section 5 of Unit 4 of AP Calculus, solving related rates problems. And hopefully we're going to get through 2 examples of solving related rates problems in this video. I don't think we'll have too much difficulty. Let's go ahead and get started. Example number 2, the width of a rectangle is increasing at a rate of 2 centimeters per second, and its length is increasing at a rate of 3 centimeters per second. At what rate is the area of the rectangle increasing when its width is 4 centimeters and its length is 5 centimeters? So I'm going to start by working my way through our little step-by-step. I'm going to draw my picture. I've got a rectangle. And in that rectangle, it has a length and a width. And we've got the whole thing, which is the area. So there's my picture of what I've got going on in this situation. And let's see what's next. So there's my picture, and I've named the variables and constants: length, width, area. All 3 of those things are changing. There are no constants in this particular problem. Then I'm going to write down my numerical information. The width is increasing at a rate of 2 centimeters per second. So that's the rate for the width. So that's going to be dw dt. It's going to be 2 centimeters per second. And its length is increasing at a rate of 3 centimeters per second. So dl dt is 3 centimeters per second. At what rate is the area of the rectangle increasing when its width is 4 centimeters and its length is 5 centimeters? So we're looking for the change in the area. dA dt is equal to what when W equals 4 centimeters and L equals 5 centimeters. Okay, so we've splashed out and done really steps 2 and 3 here. We've written down all our numerical information, and we've written down what we're asked to find. We're trying to find the change in area with respect to time. So next, I want to write an equation that relates the variables. And looking at the variables I've got here, let's see, I see W, both in a dw dt and in a w. I see L, and I see A. So we want a formula with A, L, and W for this rectangle put together, and I think most of us know that the relationship we're looking for is that the area is equal to the length times the width. Okay? Now again, make sure you follow the bold urging in step 4. Do not substitute non-constant numerical values before differentiating. All these lengths are non-constant. They are changing. The width is changing. The length is changing. Those are not constants, and so we cannot substitute them in until after we've differentiated this. So now let's differentiate this with respect to t. We've got dA dt is equal to L times the derivative of W, which, since we're differentiating with respect to t, is dw dt, plus W times the derivative of L. There's our derivative, and now we can find dA dt by just substituting in the values that we've got. L is 5, dw dt is 2, W is 4, dL dt is 3, and that gives us that dA dt is equal to 22. Now I need some units on here. The area in this problem is measured in square centimeters, and the time is measured in seconds. So my units are going to be square centimeters per second. So we end up with 22 square centimeters per second as the change in area with respect to time, which is what we were looking for. All right. On to example 3. 2 boats are approaching a buoy along paths that make a right angle. The first boat is 160 feet from the buoy and is traveling at a rate of 30 feet per second. The second boat is 135 feet from the buoy and is traveling at a rate of 35 feet per second. Find the rate of change of the distance between the boats. So I have boat number 1. I am definitely not an artist. Don't mind my boats. So we've got boat A that's traveling towards a buoy. put the buoy right here, and boat B also traveling towards the buoy. And those two boats, I am the worst artist alive, those two boats are traveling closer and closer to the buoy, which is right at this right angle intersection here. Okay, let's let A stand for the distance that the first boat is from the buoy, and B stand for the distance that the second boat is from the buoy, and then we have this imaginary line here, which is the distance between the two boats, which I'm going to use C to represent that. And so there's my picture. I've drawn a picture, and I've named the variables that are in the picture. Now I'm going to write down the numerical information in this problem. Okay, so at the moment that we're concerned with, where we're trying to find the rate of change, the first boat is 160 feet from the buoy, and dA dt, now this is a tricky one. This is a tricky one. dA dt, as time goes by, this boat is getting closer and closer to the buoy. So as time goes by, the value of A is actually decreasing, which means that dA dt is not 30 feet per second, but rather that it is negative 30 feet per second, because A is getting smaller as time goes by. Okay, B is given to us, it's 135 feet, and dB dt is equal to 35 feet per second. But again, as that boat gets closer to the buoy, the value of B is decreasing, so dB dt is going to be negative 35 feet per second. And what am I looking for? I'm trying to find the rate of change of the distance between the boats. So that's the rate at which C is changing. That's what we're trying to find. All right. Got all that laid out. Now I'm going to write an equation that relates the variables. Again, it's the oh so common Pythagorean theorem that sets us up here. And again, don't substitute anything in because nothing here is constant. Don't substitute anything in until after we've differentiated. We're going to take the derivative of this with respect to t. Gives us 2a dA dt plus 2b dB dt equals 2c dC dt. And this is something that I haven't done in any of the problems up to this point. I want to solve this for dC dt since that's what we're looking for. So I'm going to go ahead and divide both sides by 2c. So that gives us 2a dA dt plus 2b dB dt all over 2c is equal to dC dt. And since I have a 2 in every single one of these, I'm going to go ahead and cancel those 2's out just because it's one less thing I've got to worry about. And I'm going to write dC dt is equal to a times dA dt plus b times dB dt all over c. And now I just need to substitute the values in order to get dC dt. So dC dt is equal to a is 160, dA dt is negative 30, b is 135, dB dt is negative 35, and c is the hypotenuse of this triangle. So if I take the square root of both sides here, c is equal to a squared plus b, square root of a squared plus b squared. And I'm not going to calculate that before I put that in here. I'm just going to put it in here as square root of a squared plus b squared and let my calculator deal with the calculations so that I don't make any kind of rounding errors or anything like that. And so now we're going to punchy on the keys of our calculator in order to find the value of dC dt. So I've got numerator 160 times negative 30 plus 135 times negative 35, close the parentheses, divided by square root of 160 squared plus 135 squared. Oops, missed the 1. There we go. Close them parentheses and hit enter. And we get negative 45.499, whether we round or truncate. Negative 45.499, yes indeed. And now we need units. The units that we need here are for the change in c with respect to time. C is measured in feet. Time is measured in seconds. So this is going to be feet per second. And there's our final answer. All right, thanks for joining me for this video with a couple of examples on how to solve some related rates problems. It's going to be really important for you as you develop your skills with related rates problems to try and tackle as many different kinds of related rates problems as you can. And I know for my students, I'm going to give you a pretty decent chunk of practice with working on related rates problems so that you can encounter them in a wide variety of different contexts and can come up with, you know, a wide variety of different strategies in solving them. And in all honesty, the template is there. The thing that changes in every problem is how do we set this original model up? And how does this original equation work? Other than that, everything we do is, you know, identical. Write down our information. What are we looking for? Set up an equation. Take the derivative of that equation with respect to t, solve for the variable that you're trying to find the value of, and then substitute in the values that you know in order to calculate it. It really is, that's it. But like I said, you need to practice as much as you can in order to get really, really good at this. All right. So that's it for this video. See you next time and have a great rest of your day.